recording now. Okay, so I'll do 1.9 and then I'll do the last one, or part 1.9. One question 9. Okay. The frequency of, we were wondering about the frequency of obtaining this particular gamete configuration from an individual that has this genotype, big A, little b, big C, little c, and then these are 14 centimorgans apart. Okay. So, you need to break this up into parts, right? Because this is like a question about linkage. And then this is a question about independent segregation, right? So you need to think of the 4 different genotypes that are possible from here, and then thinking about independent segregation with respect to this other gene. Remember, you all definitely remember that semicolon means it's on a different chromosome. Okay. So the 4 genotypes, big A, big B, little b, big A, little b, little a, big B. Okay, 14 centimorgans. So that means a recombination frequency of 0.14. All right, so 0.14 for these ones, and then 1 minus that, 0.86 for these ones. So, you split that in half, right? You split the difference. So 0.07 for that group, 0.07 for that group, 0.43 for that group, 0.43 for that group. Okay, but that's just, but which one are we looking for? We're looking for this genotype. All right, so we're looking for that genotype here. So big A, big B probability is 0.43. Right, but there are 2 possible outcomes with respect to C, right? And, big C, little c, there's a 50-50 chance of either one. So 0.5 chance for getting that one. And since they're segregating independently of one another, it's 0.43 times 0.5. Which is equal to 0.215. I guess I wrote it as a percent there. Okay. All right. So, yeah, that's that one. That person may have left. I'm going to go through number 5 now. And this is like a Bayes rule problem. It's sort of broken up into parts. So I'm actually going to draw this pedigree out on the board. So actually, I'm going to read this to myself first. In Drosophila, the genes Cinnabar and Brown on the 2nd chromosome, Cinnabar and Brown indicate the recessive alleles. Plus can be dominant wild type. Only flies that are Cinnabar Brown have white eyes. All the genotypes are red eyes. Percent recombination is 20%. Okay, consider what is the probability that individual I is Cinnabar Brown over plus? All right, I guess that's without knowing anything about A. Okay, and then in the last part, it's like, oh, okay, what's going on? If you know something about A, then what does that tell you about the linkage relationships in I? Okay, so we have this configuration plus Cinnabar Brown and then we have individual I. And then, okay. This individual is Cinnabar Brown over Cinnabar Brown. And then there's two progeny. There's individual A, which we're going to ask some questions about. And then there's a sort of second progeny that we don't know much about. Okay. All right. What is the probability that I is Cinnabar Brown? So this is basically, without knowing anything about A, because in part A, it doesn't specify anything about A. So what's the probability that I is Cinnabar Brown, right? So we know that this individual transmits plus alleles, right? So plus. So really what we're asking is about what is the gamete that this individual transmitted. Okay. So, again, 4 possible gametes that this individual can transmit. There are the parentals, which are plus, and Cinnabar Brown together, right? And the recombinants, which are now plus with Brown or Cinnabar with plus. Okay, so plus Brown or Cinnabar with plus, right? And so the question is, what's the probability that this individual inherited that gamete right there? That in order for this individual to have that genotype, that's what would be required, right? So let's erase that for now. Okay, the recombinants are 0.2 frequency. The parentals are 0.8. Okay, and so again, we split the difference. So 0.4 here, 0.4 here. That's the one we're interested in. So the probability, I'm going to write it here, the probability that I is equal to this Cinnabar Brown over plus is equal to 0.4. Okay. But it's not the only scenario, right? I mean, I think what we're going to need to try to think about here is like, if this individual here is going to have like white eyes, it can only happen if that's the case, right? Because if any other configuration is transmitted from this individual besides Cinnabar Brown, then there's no way that this individual is ever going to have white eyes, right? Yeah, because you have to have both of these alleles. Any of these other combinations, this one, or this one, they're never going to have white eyes ever. Okay, so that's part A. Okay, what is the probability that the first progeny designated A as white-eyed? All right, so this we know has collected little cn, little bw from data over here. I'm going to erase this. And then we think maybe this individual could be this, right? The question is, what's the probability that A basically has white eyes? So in order for A to have white eyes, this had to be the case. Had to have inherited the 2 alleles together. Okay, so one way of thinking about this, I'll sort of do the short, quick way, and then I'll do sort of the longer way, is to just say like, okay, there's a series of events that has to have happened. The first has a 0.4 chance of having happened, right? And then if this in fact is of that genotype, then it's the same probability as before. So then, you have to transmit the CNBW chromosome again, right? So the first time is 0.4, and then the second time is 0.4. Right? And so it was 0.16. So that's kind of like a quick and sort of shorthand way. And I've done that kind of thing before in class where it's like, you have this sort of like iterative probability and you're asking like, what's the probability that like this series of events have happened down a lineage within a pedigree? And the probability that, that allele gets transmitted to the first offspring, and then the probability that if that was transmitted to the first offspring, that it gets transmitted again. And it's sort of this chain of probabilities. That sort of framework is derived from the law of total probability. And I'll break it down sort of in a way in that framework, which may be a little bit more intuitive, but I kind of like to think about it this way. So what we're going to do here is we're going to say the probability that this individual here has this particular genotype is going to depend on if this configuration is in this individual or not, right? So it's going to basically, we're going to set it up with, we're going to say, what's the probability that individual A is equal to Cinnabar Brown over Cinnabar Brown, right? And that's going to be equal to, all right, the probability that individual A is equal to Cinnabar Brown over Cinnabar Brown. And this is sort of like this, like, what's the probability of getting cancer, lung cancer, given that you're a smoker, times the probability that you're a smoker, times, added to the probability that you get lung cancer, given that you're not a smoker, times you're not a smoker, right? The probability of A is equal to the probability of A given B times the probability of B plus the probability of A given not B times the probability of not B, right? That's the law of total probability, but I'm going to break that out in here. So the probability that this in fact happens is going to be the probability that this happened given I is equal to this particular genotype, Cinnabar Brown over plus plus, times the probability that that is in fact true, that I is equal to Cinnabar Brown over plus plus. And that's going to be added to the probability that A has this particular genotype of interest, Cinnabar Brown over Cinnabar Brown, given I doesn't have that genotype. I is not Cinnabar Brown over plus plus. And there's a lot of ways, there's three ways for that not to be true, right? It could be plus plus, it could be plus Brown, it could be Cinnabar plus. There's three possibilities. But if you think about it for a second, if any of those three possibilities is the case, this is never going to be Cinnabar Brown over Cinnabar Brown, because this has to be the case for this to be true. Okay, so what's the probability that that individual is not of that particular configuration? Probability I is not Cinnabar Brown over plus plus. All right, so let's put these through. All right, what's the probability that this individual I has that genotype? We said it was 0.4. All right, and then if this individual has this particular genotype, what is that probability that it transmits the Cinnabar Brown again? Well, it's 0.4, right? Which you'll remember we already did. We did 0.4 times 0.4. We've already done that. Now, the next question then becomes, this is going to get added to, okay, this is the probability of A being Cinnabar Brown over Cinnabar Brown, given that its individual doesn't have that genotype. Now, if this individual doesn't have that genotype, put this in the chat. What's the probability that this individual will have the white eyes under that condition? Yeah, 0. It can't happen. Great, thank you. So this becomes 0. And now, it doesn't matter what's here because this is multiplied by 0, but you should be able to say the probability of not having that genotype is the 1 minus the probability of having it, right? It's the probability of being plus plus the probability of being Cinnabar plus the three other possible genotypes. It's 0.6, but it doesn't matter, right? The whole thing, the only thing that matters is 0.4 times 0.4. So basically, this allele gets transmitted in the unrecombined state, and then that allele again gets transmitted in the unrecombined state, 0.4 times 0.4. Okay, so that's part A and B. And then the tricky part, with respect to Bayes' rule, I think is in part C. Okay, so I'm going to erase this. I'm going to erase this because I need some working area here. Okay, this was that, right? I'm going to erase that here. Okay, now what happens though is that the first progeny is red-eyed. All right. So that means that not this allele, Cinnabar brown, is not transmitted. And you might say to yourself, okay, the fact that this individual is red-eyed, the fact that this individual is red-eyed, you know, it might reduce the chance that this individual has that genotype. Although you could see that this individual could have that genotype. And still that individual be red-eyed because there could be a crossover here. So, you know, what this is, just a reminder when you're thinking about Bayes' rule, is that we have some information about a condition, and this is a condition that this individual is under. Now, if we had a lot of outcomes, we would have more and more feeling about this particular genotype. So when you see basically a thing where you're like trying to kind of back calculate the probability of a condition based on an outcome, you should think that you're going to need to use Bayes' rule in this particular framework. Now, the framework is written, I guess actually it's all on the answer sheet there. I guess I could walk through it. Yeah. What we want to do is we want to figure out the probability that this individual actually has that genotype, because we're going to ask something. Because the question is, if this has red eyes, then the question really becomes, you know, what's the probability that this individual is white-eyed? In fact, has that genotype. And that's clearly going to depend on the probability of whatever I is. So what we want to do is kind of come up with a revised probability. And so I'm going to write that here. I'm going to condense this a little bit. We want to know the probability that I, in fact, does have this thing that's of interest, right? Which is this configuration given, all right, that this individual A ended up with red eyes, right? And so the way that, I mean, there's three ways that this individual could not have red eyes, but let's just keep it simple and just say that A is not equal to, I'll just use like a not equal to Cinnabar brown over Cinnabar brown. Because there's three ways for that to be the case, and I think if we keep it simple this way, it might help. All right. So we want to know what's the probability that this individual has this genotype. So that's why I break this up into part 1 and part 2. Part 1 is figuring out, okay, like I have this outcome. I want to come up with my revised probability. Originally, I thought it was 0.4, but it's going to be different now based on this outcome. And then once I have that, I'll use the law of total probability to then recalculate the probability of this particular outcome. All right. So the probability that this individual I has that configuration, given that this individual is not Cinnabar brown, is going to be equal to the probability that that individual is not Cinnabar brown, given I does have that configuration, times the probability that I has that configuration. Right, there's the prior right there. Okay, and then that's going to be all over. Okay, so then this is just going to be this repeated, right? I'll just remind you just how we frame Bayes' rule. The probability of A given B is equal to the probability of B given A times the probability of A, all over the probability of B given A times the probability of A, plus the probability, when there's two outcomes, B given not A times the probability of B given not A. So we're going to kind of think about it in that framework. So, you know, this is A right here. And then this is B. Okay, so, and those are numbers that we know, right? A and B, but we can kind of figure out these separately. Okay, so this whole thing is repeated, right? So this is here and here as well. So we're gonna say the probability that we have this outcome A not being Cinnabar Brown, not Cinnabar Brown, given I is equal to Cinnabar Brown over Cinnabar Brown, becomes the probability that that in fact is the case.
I thought I had to have plus plus on the bottom.
Oh, thank you. You're right. Yeah. Okay, yeah. Did I fix that completely? Yeah. Okay. And then we're gonna add that to, and you'll see that, things kind of get simpler in a moment. The probability that A, again, doesn't equal the Cinnabar Brown genotype, which means that they have red eyes. Given now, and then this is the thing where I doesn't equal to Cinnabar Brown over Cinnabar Brown times the probability that I doesn't in fact equal that. Equal, like I'm putting that not. Sorry, I did it again. Cinnabar Brown over plus plus and Cinnabar Brown over plus plus. Okay, yeah. Okay, let me make sure that that's all right, because sometimes I get ahead of myself here, and I make a dumb mistake. Oh yeah, that looks like what I have all here. Okay, it looks like here I have the plus plus and the Cinnabar Brown switch top and bottom. It doesn't matter. Okay, so we're trying to figure out if this individual has this particular genotype, which is mandatory for this individual to be white, given this particular outcome that this individual had red eyes, which mean that it didn't inherit the Cinnabar Brown chromosome. Okay, so let's walk through. I'm going to erase this because I need to there's some space I need to work through here. Okay. This here, what's the probability that this individual in fact was Cinnabar Brown over plus plus? That's just the prior without any information. And we've already calculated that, right? Because this individual here was that genotype. Make sure I don't do something there. Yep. And so we said that the chance that I would then be of that genotype would be 0.4. Okay, now if this individual does in fact have that genotype, and then the probability that this individual isn't Cinnabar Brown, right? So that's not 0.4, because 0.4 would be the probability that it did transmit the Cinnabar Brown. This means it didn't transmit the Cinnabar Brown, so it's basically 1 minus that. 0.6. Okay. Basically ended up with red eyes, even though this individual still had the Cinnabar Brown together. Right. So all of the other three genotypes, one of the three genotypes was transmitted instead of the Cinnabar Brown chromosome. Okay, so then this becomes 0.6 in here as well. Right. And then this is still 0.4 here as well. Okay, now what's the probability that this individual I isn't fact of that configuration, Cinnabar Brown over plus? It's 0.6 again. Sure, I'm making any stupid mistakes. All right, now if this individual doesn't have that linkage relationship, or excuse me, doesn't have that genotype, can this individual ever have white eyes? And the answer is no. It doesn't have to have, there was a question. Doesn't I have to have plus plus on the bottom? Okay, that was the question.
You already answered that.
Okay. So, that's guaranteed, right? If this individual doesn't have that particular genotype, then this is definitely going to be the case that this individual doesn't have white eyes. So this is going to be 1. Right, and that's, yeah, that's what I have here. So that whole thing becomes 0.24 divided by 0.84, which I'm actually going to reduce for the heck of it right now. 0.24 divided by 0.84, 0.2857. 0.2857. Okay, so, you know, before we said it was a 0.4 chance that this individual had that genotype, but because this individual didn't inherit, didn't have the white eye phenotype, our probability for I having that particular configuration has gone from 0.4 to 0.2857, so it's reduced. All right, that's part 1. I mean, that's like 99%, well, maybe 90% of it, right? So we have this new probability now. We have now the new probability. Sometimes it's called the posterior. The probability that I is now, I'm going to keep it short, plus over Cinnabar Brown, like that, is equal to 0.286. I'll just round it. Okay. Now the question is, okay, what's the probability that this individual then ends up with red eyes? All right, so let's call it white eyes, excuse me. The probability that that individual ends up with white eyes. So the probability that question mark, right, is equal to Cinnabar Brown over Cinnabar Brown is equal to, and now we're using the law of total probability because we're reconditioning on this new revised chance of this individual having the suitable genotype that is mandatory, in fact, for this to have white eyes, or the alternate, you know, which if it does have the alternate, there's no way it has white eyes, right? So shorthand, we could just say 0.286 times 0.4, right? Because this has to happen, and then the 0.4 event has to happen. We could be short about it, and then that would be the answer. Or we could be a little bit verbose about it and say the probability that this, in fact, is the case is equal to the probability that question mark equals Cinnabar Brown over Cinnabar Brown, given I is equal to plus over Cinnabar Brown times the probability that that's actually the case. Probability that I is equal to Cinnabar Brown. Sorry, I'll just keep the same. Plus over Cinnabar Brown. All right, plus the probability that the probability that question mark is in fact white-eyed, which would be Cinnabar Brown over Cinnabar Brown, given I doesn't equal that configuration. I is not plus over Cinnabar Brown times the probability that I is not plus over Cinnabar Brown. Okay, now if this individual, what's the probability that I in fact has that configuration? Well, we recalculated it, right? We said it was 0.286. Now, if that individual has this particular configuration, what's the probability that that individual transmits the Cinnabar Brown chromosome? Well, we've calculated that a bunch of times. That would be 0.4. Right. Now, what's the probability that this individual, I should have said not, excuse me, that this individual doesn't have that relevant genotype? Well, it'll be 1 minus 0.286, which is 0.714, I think. Yeah, that's right. Right. Now you could say like, well, why did you bother calculating that one? Because this one here, what's the probability that we end up with white eyes given that this individual doesn't have this focal genotype that we're of interest in, right? Well, that's just going to be 0 then. So that's why sort of a shorthand is just to say 0.286 times 0.4 and So whatever that is. Okay. I am already going to stop recording and then post